Hello students, welcome back to SapphireBlueChemspark. Let us start our today's session, the chapter Coordination Compounds from Inorganic Chemistry. We completed most of the topics of the coordination compounds in our previous sessions. Today we are in the end of the chapter. So we may find the first one, stability of coordination compounds. Actually, coordination compounds are formed by the reaction between the metal and the ligand. So, during the formation of the complex, the bond between the metal ion and the ligand is very strong. Then the stability of the complex will also be very high. So, though the complex salts are extremely stable in nature, they may undergo dissociation to some extent in aqueous solution. So, let us find the dissociation of complex salt in aqueous solution. We may get the dissociation of complex, it gives rise to metal ion and the ligand ion. So, as it undergoes the dissociation, where it does not make the complete dissociation, it has the partial dissociation only. Because of the partial dissociation of the complex into its ions, there would be an equilibrium between the dissociated and the undissociated one. So, for such equilibrium, we can calculate dissociation constant for the complex. So, we can write the dissociation constant of the complex is the product of concentrations of products divided by product of concentrations of the reactant. And we know here the dissociation takes place for the complex, and hence the dissociation constant can also be termed as instability constant. If I want to know what is the stability of the complex, what I can do? I can take the reciprocal of dissociation constant. So, reciprocal of dissociation constant will become the stability of the complex or the formation of the complex, and hence I can make the reciprocal of the value. So, from this we can identify the instability constant of the coordination compound is defined as the reciprocal of formation constant, because we can rewrite the one, or Ki is equal to 1 by Ks. So, we can define both instability constant as well as stability constant of the complex. Now, we can compare what about that value of Ks, that is the stability constant. In stability constant, you may find the formation of the complex is in its numerator. So, when stability of the complex increases, the stability constant increases, stability of the complex is also increases. So, let us find the example of the formation of the complex. Let us going to take an example of the complex having coordination number 4. Because why do we take from the stability constant? We may find what type of ligands can give more stable complexes. So, we can calculate stability constant for the different complexes. Based on the data of Ks value, we may find out which of the ligand can provide more stability to the complex. Okay, let us take an example of the type ML4. We are going to take the example of the type ML4. So, in this case, the metal, it reacts with 4 ligands to form ML4, and this is the overall reaction of the complex formation. We can take the stepwise reaction of this one. So, the first step, metal ligands with 1 mole of ligand. Metal reacts with 1 mole of ligand, it forms Ml. So, for which K1 equal to Ml, concentration of Ml divided by concentration of M into L. And then second unit of ligand I am going to add. So, what I had to take? Ml plus L, that gives Ml2. For this, the second formation constant is Ml2 divided by Ml into L. Or else I can take the third step, Ml2, it reacts with 1 more mole of ligand to form Ml3, where K3 is equal to the product of concentration of product divided by product of concentration of reactant. and the last step, the Ml3 reacts with 1 more mole of the ligand, it forms Ml4, for which K4 equal to Ml4, concentration of Ml4 divided by concentration of Ml3 into concentration of ligand. So we have taken the 4 different constant. Suppose if I take that stability constant for the formation of overall complex, what I may write? Beta 4 is equal to concentration of Ml4 divided by concentration of M and concentration of L to the power 4. This is why, because the power is nothing but how many times the ligand takes place in the reaction. So this beta 4 is said to be stability constant, or it is formation constant. So in this case beta 4, I have to take down the stepwise equilibrium constant or the stepwise stability constant. So we can have the 4 represents the coordination number of the complex. So beta 4 is equal to the product of formation constant of every stepwise reaction. So I may find beta 4 equal to K1 into K2 into K3 into K4. Here I have taken the ligand only up to 4. Suppose if I take n times of ligand, then it will become beta n equal to the product of formation constants of all the stepwise reactions. Next, if I take log on both sides, what happens? In the logarithm, when you find the product, you have to make it as a addition value. So the rule we have, according to product rule of logarithm, log mn is equal to log m plus log n. So applying the product rule, taking log on both sides, I can write log of beta n equal to log of entire values, formation constant. So applying that product rule, I can write log k1 plus log k2 plus log k3 etc. plus log kn. So to explain about the stability of the complex, let us take an example. Formation of tetraamine copper 2 sulfate is taken. We need to take the stepwise formation of the tetraamine copper 2 plus ion. For every step, we are having the log of K1, K2, K3, K4. For the first step of formation of complex, K1 is 4.0. For the second step, that amine complex reacts with 1 more mole of ammonia, it forms diamine, for which log K2 equal to 3.2. To the diamine, I can take 1 more mole of ammonia, it forms triamine. In this case, log K3 equal to 2.7, and the final, it reacts with 1 more mole of ammonia to form tetraamine, for which K4 equal to 2.0. What I said? The stability constant log of beta n is equal to the sum of formation, logarithm of formation constant of all the steps. So here 4 steps I have, that's why the stability constant log beta 4 equal to sum of all these 4 values, that makes 11.9. So comparing, the stability constant is high and hence the complex is said to be more stable. The next one, factors affecting the stability of the complex. There are 4 factors which may influence the stability of the complex. One is the nature of the metal ion, nature of the ligand, and crystal field effect, followed by class A, class B metals. So let us find first of all the nature of central metal ion. Already we know, depends on the charge of the metal ion, the stability of the complex is determined. The transition metal, they do have their variable oxidation state. So when the same metal ion in its higher oxidation state able to form the more stable complex than in its lower oxidation state. This is why, because when the charge density increases, the size of the metal ion decreases, the polarizing power power and the approach of ligand, splitting of d orbital will also be favored. This is why we may say the metal ion with higher oxidation state able to form the more stable complex. We may find the example, the complex of the type iron. In one case the iron it is in +3 oxidation state, the other case the iron it is in +2 oxidation state. So in the +3 oxidation state of the complex, the stability constant is given by 1.2 into 10 power 31. At the same time, the iron 2, it makes the stability constant of 1.8 into 10 power 6 only. The next one, suppose if I have different metals but having the same charge, then how it would be the stability of complex? This depends upon the size of the metal ion. So in a period we know that when the nuclear charge, that is the effective nuclear charge increases, size of the ion decreases. So along the period when we consider the metal which is at the end of the series will form more stable complex because of its very smallest size. So we can compare the 3D series of the element iron 2 plus, copper cobalt 2 plus, nickel 2 plus, copper 2 plus is taken. Copper is the end of the 3D series. So copper it is in its smallest size and hence copper complexes are more stable. The next one, nature of ligand. When we speak about the ligand, we have unidentate ligand, polydentate ligand, and we have the neutral ligand and the negatively charged ligand, even positively charged ligand. And we may have even the ligands are having the tendency to form a chelates with the metal ion. So based on its qualities, we may find the 4 different categories of nature of ligand. The basic character of ligand, we may say more the basic character, more the stability of the complex. So when we compare the 17th group complexes, 17th group is the halogen family, in which the fluoride complexes are more stable than chloride complexes. This is why, because on going down the group, metallic character increases. So the electropositivity increases down the group and hence the metals or the elements at the top of the group can have the more stable complexes because of their high electronegativity. The next one, charge on ligand. The ligand, if they have higher charge and the size of the ligand is smaller, then they able to form stable complexes. Then chelate effect. We have the bidentate ligand and we have unidentate ligand. The bidentate ligand that can connect the central metal atom or the ion through its 2 of the donor atom. But in the case of unidentate ligand, it can donate its electron through only one of the atoms of the group. So when the denticity of the ligands increases, the chelate effect also increases and hence the stability of the complex also increases. So we may find tris ethane 1,2 diamine nickel 2 plus ion whose stability constant is 18.1. But hexaamine nickel 2 plus ion stability constant is simply 7.99. This is why, because the En is a didentate ligand and hence it can form a chelate effect. The next one, macrocyclic effect. In this case, the ligands itself have a cyclic one and the cyclic form which is free from the steric effect, able to form the more stable complexes. So in some cases the ligands they themselves make a cyclic effect with the central metal ion. Those will be the multidentate ligand. For example, EDTA we can say. EDTA is a hexadentate ligand, but EDTA has no any closed cycle. It is a open chain only. Besides EDTA, we may have the ligands themselves have the cyclic structure and free from steric effect can give more stable complexes. The next one, crystal field effect. Crystal field effect is given by Irving-Williams order. So in this case, the stability of the complex depends on size of the central metal ion. Already we discussed the size. If at all smaller, then the stability of the complex will be very high. So we can take the 3D series of the element from manganese to zinc. We may find the size of the metal ion goes on decreasing, and hence the complex of the zinc will be more stable than the complex of manganese. Also, the charge to radius ratio of this metal ion is found to be consistent. That means there is no much variation in their value. So, as they have the similar charge to radius ratio, then the stability of the complex is also known as more. And we may say this order is called natural order. This Irving-Williams order is also known as natural order. The next one, class A, class B metals. The class A, class B classification, it is simply based on the periodic table. Here I have given hydrogen. Hydrogen itself form a ligand type only, that is the hydride ion. Except hydrogen, we have to consider the 1s group element, those are alkali metals, and 2s group elements are alkaline earth metals. Besides these two group elements, we are having the elements of the third series, aluminium to chlorine, and the fourth series, scandium to chromium, and in the same series, fourth series, zinc to bromine, indium. Zinc to bromine we have to consider. In addition to that, indium, antimony, tin and iodine, they do form stable complexes with the ligands containing fluorine, nitrogen, oxygen groups. Class B elements, besides these class A, those are said to be class B. In this class B elements, they have their fully filled d orbital. Though zinc has fully filled orbital, it becomes the exception to class A. But the other elements, rhodium, palladium, gold, silver, platinum, iridium and mercury, they do have fully filled d orbital but form stable complexes with the ligands of the groups of higher member of oxygen, nitrogen, fluorine family. The next one, borderline. Borderline, exception of class A and class B, rest of all the metals belong to borderline, and these complexes do not have any particular stability order that may vary. So that those elements are said to be borderline elements, and those metals are manganese to copper, molybdenum, tellurium, ruthenium, tungsten, etc. Okay, so we classify the metals into class A, class B and borderline, and we said these metals or this group of elements can have their complexes with the ligands containing fluorine, nitrogen and oxygen. So how the stability of those complexes will be there, that can be given in two different ways. The first one, stability order of class A elements with the ligands containing fluorine, nitrogen, oxygen group I am saying. So the fluorine group is halogen family, nitrogen group is nitrogen family and the oxygen group is oxygen family. So when I have that halogen family where the halide ions, they show the regular trend, fluoride greater than chloride, greater than bromide, greater than iodide, followed by 16th group element, oxygen greater than sulfur, greater than selenium, greater than tellurium, which is followed by the 15th group element, nitrogen, which is much greater than phosphorus, arsenic, antimony and bismuth. So if at all I say about the formation of complexes with these groups, for the class B elements, the order exactly be reversed. So instead of writing greater than, we have to write less than. So that's all. These are the factors that may affect the stability of complexes. The next one, metal carbonyls. Metal carbonyls are an important class of coordination compounds in which the carbon monoxide is alone the ligand to donate its lone pair of electron to the central metal atom. In all these complexes, the metal atom is found to be in zero oxidation state. Nickel tetracarbonyl. This is what first prepared by Ammon in 1890. And these complexes probably homoleptic complexes because the complexes are made up of only the ligand type of carbon monoxide alone. Classification of metal carbonyls. Metal carbonyls can be classified into two types. One is depends on the number of metal atoms present in the complex. Can be said to mononuclear carbonyl or polynuclear carbonyl. The other one is based on its structure. Let us see first of all the classification based on number of metal atoms. We can have mononuclear carbonyls and polynuclear carbonyls. Mononuclear carbonyls are made up of only the one metal atom with its ligand. Polynuclear carbonyls, they can have more than one same metal atom or the different metal atom with its ligand. So, for the mononuclear carbonyl, we can have the example of the type tetracarbonyl nickel or hexacarbonyl chromium. And in polynuclear carbonyl, in one of the complex, we have both manganese and cobalt are present. But in the other case, the iron itself present thrice the time. So, when the metal is present more than one time of its same type or the different, those are said to be polynuclear carbonyl. The next one, the classification of metal carbonyl based on structure. The structure, they can have either bridging unit of carbonyl group or the non-bridging carbonyl complexes. Suppose if I have pentacarbonyl iron or tetracarbonyl nickel, they can be given like this without any bridging unit, all the carbonyl group that can lie on its plane. So, the first one is nickel tetracarbonyl, it has a tetrahedral shape, and the other one is pentacarbonyl iron, it has trigonal bipyramidal shape. So, these complexes are the examples of non-bridged structures. So, in all these type, we do not find any bridging group. The bridging should be made up of only the carbonyl group. Such bridging atoms or the nucleus is not there. So, these three class, they belong to non-bridged metal carbonyl. If I take Fe2CO9 here, iron twice the time present and there are 9 carbonyl group. So, these 9 carbonyl groups should be shared between the 2 iron atoms. So, the 2 iron atom, they have the link of iron-iron linkage, to which 3 of the CO groups are in non-bridged condition and one more CO group that makes a bridge between the iron-iron and 2 more CO group that makes 2 more bridges with both of the iron atom. Such type of structures belonging to the bridged metal carbonyl. So, this belongs to the type of bridged metal carbonyls. So, these are the classification of metal carbonyls. The next one, nomenclature of metal carbonyl. We have the metal carbonyl with mononuclear carbonyl as well as polynuclear carbonyl, and we have the structures of the bridged structure also. So, in such conditions, how to name the complexes? Suppose if the complex is a mononuclear complex, then the name is as, just like we have to follow the IUPAC rule. We can say how many times the carbon monoxide group is there, to which what is the metal atom, we can write tetracarbonyl nickel. And I said that metals are in its zero oxidation state. So, the name is tetracarbonyl nickel. or it is hexacarbonyl chromium, and we can write their oxidation state as 0 in near to metal atom. Because according to IUPAC nomenclature, the oxidation number to be mentioned for the central metal atom or the ion. Suppose if we have the bridging nuclear and in the case of polynuclear carbonyls, how to name the one? So in this condition, you can identify the bridged structure. Here the two metal atoms which are linked together, such linkage is referred as bis. Why it is bis given? Only two metals are there, that's why it is said to be bis. Suppose three metals are there, then it is called as tris. So this is for the linkage between the metal atom. Or if we have any bridging carbonyl group, that bridging carbonyl group is termed in terms of mu. So how many carbonyl groups are in bridging? I have 1, 2, 3. So there are 3 bridging unit of carbonyl. So it is said to be mu tris carbonyl. So the name is tris mu carbonyl. That means 3 carbonyl groups are in its bridging structure. And I have 2 metal atoms which are directly bonded to each other. 2. That 2 is said to be bis. So it is called bis. And each ion, they have only 3 carbonyl group. The non-bridged groups are 3 times only present. So it is bis tricarbonyl ion. So the bis refer to the number of ion present in the complex, and the tricarbonyl which are the free carbonyl group that link to ion. So for the bridging and polynuclear structure, the bridging is referred in terms of mu, and the polynuclear always termed as a bis tris, like that. Because we have how many times the carbonyl are there, that we are using their prefixes. So to avoid the prefixes confusion, we have to make use of bis tris for the number of metal atom present in the complex. Okay. So in these cases, the complexes are made up of only carbonyl group. The other cases, I have carbonyl group. In addition to that, the group is there having a pi bond. So in this case, I have benzene. Here C4H6 is butadiene. Benzene, it has 3 pi bond. Chromium, that can make the coordination number of 6. So in such cases, chromium, 3 of the coordination number is satisfied by the 3 carbonyl group, and 3 more coordination number is satisfied by a benzene ring. So the presence of pi bond in a complex is always referred as hapto. That symbol is referred as hapto. This is called hapto. And in this hapto, we have to mention how many carbon atoms are there in its ligand. There are 6 carbon in the benzene. So it is called hapto 6 benzene tricarbonyl chromium. Suppose if I have the complex of iron pentacarbonyl. See, iron pentacarbonyl, only 5 is the coordination number. So 3 of the coordination number satisfied by the carbonyl group, and 2 of the coordination number satisfied by its double bond. Because butadiene, the formula is CH2 double bond, CH double bond, CH2. So these 2 pi bond becomes the coordination number of the ion. So in this case, this is also a pi bond containing group, and hence it is termed as hapto. And the hapto having the number of carbon 4. So hapto 4 butadiene tricarbonyl ion. This is the way we have to give the IUPAC name for carbonyl compounds. The next one, bonding in metal carbonyl, such a most important concept. In metal carbonyls, we have 2 types of bonding. One is the ligand to metal bonding, The other one is metal to ligand bonding. So here one bond is actually formed by the ligand to metal is sigma bond. Besides the formation of sigma bond, one more bond is formed from the metal to carbon, that is said to be pi bond. So due to the formation of both sigma as well as pi bond, these carbonyl complexes have extraordinary stability. So we may find how the sigma bond and pi bonds are formed. The carbonyl group, they have their molecular orbital diagram. According to molecular orbital theory, we can write the electronic configuration for carbon monoxide. Actually it has 6 plus 8 electron, so totally 14 electron. That makes a sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Then sigma 2pz2, after that pi 2px2 equal to pi 2py2. Then later on pi 2px star, pi star 2px equal to pi star 2py. So in this case we may find total number of 14, 4, 8, 12, 12 plus 2, 14. So here the filled orbitals are present in s orbital, z orbital of p, z orbital and px, py orbital. But the anti-bonding orbitals of carbon monoxide is empty. So now let us find the carbon monoxide. It has a lone pair of electron over the carbon as well as a lone pair of electron over the oxygen atom. But it has a tendency to donate its pair of electron from the carbon donor. And hence the filled orbital of carbon that donates electron to the empty vacant orbital of metal atom, and hence it forms the metal carbon sigma bond through their axial overlapping or head-on overlapping. So the 2 electron which is present in the carbon that donates its vacant orbital of metal, it forms the carbon to metal sigma bond. Now the metal, it has filled d orbital because the carbon monoxide that can forces all the d orbital electron and s orbital electron together in the d orbital itself. Therefore the metal d orbital have filled d orbital electrons. The filled d orbital electron, it can give its electron pair to the anti-bonding pi star orbital of carbon monoxide. Here we have the anti-bonding pi star orbital of carbon monoxide. To this vacant orbital, the filled metal orbital can donate its electron, and hence that makes a pi bond between metal to carbon. So besides the formation of sigma bond, there is a back bonding takes place between from metal to carbon. Such bonding is said to be back bonding or back donation. Therefore, the carbonyl complexes are stabilized by both sigma bonding as well as pi bonding, and hence it produces a synergic effect, that is for the strengthening of the metal carbonyl complexes. So it can be represented all together. The metal, it has filled d orbital, and the carbon, it has filled orbital of p electron. So the carbon also have pi star anti-bonding. The carbon, it donates its filled electron to vacant orbital of metal, that makes sigma bond, and the filled d orbital of metal donates its electron to the pi star anti-bonding orbital of carbon, that makes a pi bond. So this creates a synergic effect between the metal and carbonyl. So the formation of synergic effect is responsible for the extraordinary stability of the complexes. The last topic of coordination compounds is applications of complex compounds. Complex compounds, they find their applications in most of the field. Let us see one by one. The first one, the complex compounds are used in qualitative and quantitative analysis. Qualitative analysis, it is useful to detect the presence of a particular metal in a given salt or the sample. And quantitative analysis, this is useful to estimate the amount of particular element present in a given sample. So, most of the chemical reactions, when we do the salt analysis, we may find the formation of colored solutions. That colored solutions are due to the formation of the complex with the suitable reagent. For example, we may find the formation of deep blue solution when copper salt is treated with the excess of ammonia in presence of alkaline medium. Then estimation of hardness of water. Complex salts are also useful in the determination of the amount of hardness present in water. Hardness of water is nothing but the saltiness of water. So that can be done by titrating the water with sodium EDTA, Na2EDTA. So in this, when the hot water is titrated with Na2EDTA, the sodium metal can be replaced by the calcium or magnesium present in the hot water. So these EDTA, calcium and magnesium complexes of EDTA, they become the precipitate, and the precipitate is filtered off, followed by estimating the amount of calcium and magnesium present in hot water. The next one, it is also useful in the extraction of metals, particularly the noble metals like gold and silver. The gold or silver ores are usually treated with sodium cyanide, where it forms the cyanide complexes of silver or the gold. These cyanide complexes followed by treatment with metal zinc, the zinc can replace the gold and silver from its complexes. So we can have the free metal atom from their ore. So that process is usually known as MacArthur cyanide process. The next one, in the purification techniques. So after the extraction of metals, the metals to be taken for its purification. So the metal like nickel can be purified by Mons process, in which the impure metal means it may have some other metals or some other non-metals also. Those that can be removed by treating with carbon monoxide, where it forms nickel tetracarbonyl, a volatile compound. This volatile compound, on heating, it gives only the pure nickel, and all the insoluble and less volatile substances will be left behind. So this is the complex compounds are useful in purification techniques also. Then in biological system, some of the enzymes and the chlorophyll, hemoglobin, vitamin, these and all are present in the form of their complex compounds. For example, the chlorophyll, the greeny matter of the leaves, which is responsible for the photosynthesis, is nothing but the magnesium porphyrin complex. The hemoglobin, that is also a complex compound of iron and porphyrin. Vitamin B12, that is cyanocobalamin, that is also a complex of cobalt. Some enzymes like carbonic anhydrase also is existing in the form of complex compound. Then its industrial applications. Industrial application, these are used as catalyst. Also it is used in the electroplating techniques, moreover in photography also. When it is used as a catalyst, we can find the one of the catalyst, Wilkinson's catalyst. It is nothing but the triphenyl phosphine rhodium chloride, that is called Wilkinson's catalyst. It is useful for the hydrogenation of alkenes. Complex compounds also used in electroplating, because the usage of the complex compounds in electroplating may give a smooth and a complete finishing of the article. We would not find any coarse deposition and all. So for the uniform coating of articles, we can make use of silver or gold cyanides. The next application in photography. In black and white photography, after the developing of film, it has to be washed with hypo solution. Hypo is nothing but sodium thiosulfate solution. So when the developed film is washed with hypo, where the undissociated silver bromide that makes the complex of thiosulfato ion. So that excess of silver bromide can be washed off by treating with the hypo solution. The last application is in medicine. In medicine, the EDTA, a chelating ligand, a hexadentate ligand, is used to remove the lead poisoning. EDTA that can make complex of lead, where it forms a more stable complex and that can be removed. Cisplatin, that is the cis form of diamine dichloridoplatinum 2, is used in the treatment of cancer, where it controls the growth of tumor. The next one, D-penicillamine and desferrioxime B. These are also chelating ligands, which is useful to remove the excess of copper or iron present in plants and animal system. That's all the applications of complex compounds. Okay students, we have completed this chapter. Hoping that you will all understand the concepts delivered in all these videos. And these videos are repeatedly posted only for the benefits of students. You may share these videos to your friend as well as foe. Okay students, let us close our today's session. Let us meet once again with the new topics of the new chapter. Until then, bye bye.